So before we solve some questions, I can write a brief summary for you guys on chapter 18, just in case you haven't covered the concepts yet. So this is our first chapter on thermodynamics, the branch of physics that deals with heat and the heat energy and the change in temperature. And we said our fundamental quantity here is temperature. If we have an object at a non-zero temperature, then we can study thermodynamic properties. If there is no temperature and no change in temperature, then we can't really study any heat energy and any of the phenomena that we saw that occur solely in thermodynamics. So we defined the temperature for a start, and we said the temperature is a quantity that we can measure with a thermometer, and we defined several units: the degree Celsius, degree Fahrenheit, and the Kelvin scale. And we learned how to convert between these three. And we also defined next the phenomena that can occur in thermodynamics. Namely, when we change the temperature, the first phenomena we saw, if we have a change in temperature, and we named that delta T, we said our first phenomena that we can see is the thermal expansion, which is the change in the size of objects when their temperature increases or decreases. And we discussed a formula, which was delta L equals alpha L0 delta T, where delta L is the change in the length. Here we are considering one-dimensional change due to temperature change. We can also consider two dimensions, and then we address the change in the area and the volume, similarly for three-dimensional expansions. Of course, the actual expansion is occurring in 3 dimensions, but I might be interested in the length of a rod and not really what's happening to its thickness. In that case, I can just use this formula. So delta L here is the change in length. Alpha is the coefficient of linear expansion. It's a constant related to the type of the material that we are studying and the one that has changed its temperature. L0 is the initial length. So the larger the object initially, the more expansion it's going to undergo for the same change in temperature. And finally, delta T is the change in temperature. So this was our first phenomena, and we also discussed our second phenomenon, which is the heat energy involved when we have a change in temperature. So again, we have some change in temperature, delta T, and there is some heat energy that will be either released or absorbed to attain this change in temperature. And we said this energy is equal to, well, Q is the symbol of the heat energy, and like any energy, its unit is joules, and our formula was mc delta T. So this is the heat energy required to change the temperature of an object by delta T. M is the mass of this object or the material that we are heating up. C is the specific heat, and delta T is the change in temperature. C is the specific heat, which is, again, a property that depends on the type of material we have. Certain materials, they don't need a lot of energy to change their temperature by, let's say, 1 degree Celsius. Namely, we discussed that metals would have a specific heat of around 900. This means if I have 1 kilogram of mass and I want to change its temperature by 1 degree Celsius, then I will need a Q of around 900, okay, to establish a change in temperature by 1 degree. For water, we said water has a larger specific heat. Water has larger capacity to absorb heat without changing its temperature. So water will need more energy to change by the same amount of delta T. Any questions on these before I proceed with problem solving? We also defined, of course, the energy involved with phase change, which we defined as m times L, where again, m is the mass of the material and L is the latent heat, which is a constant related to phase change. So let's check our first question. So we have here some temperature in the Siberian village of Oymyakon. So this temperature is minus 71 degrees Celsius. We want the temperature in the degree Fahrenheit scale. As I told you before, this temperature, the degree Fahrenheit, it's mostly used in the US, and otherwise we use degree Celsius in Europe and Asia. So to convert between the two, we are given that the degree Fahrenheit unit is equal to 9/5 times the degree Celsius unit plus 32. That's how we convert between these two units. So if I'm given the temperature in degrees Celsius, I'll just substitute that here. I'll put minus 71 plus 32, and I'll find the degree Fahrenheit unit. You will get minus 96 degree Fahrenheit. One interesting thing about the degree Fahrenheit is on the scale itself, on the thermometer, you have more divisions. So the value which is in degrees Celsius will always look smaller because of the larger number of divisions on the thermometer of the degree Fahrenheit scale. Okay, now we have the other way around in part B. We're given the temperature in degree Fahrenheit and we want it in degrees Celsius. So what I would do, rather than having to worry about two formulas of conversions between Fahrenheit and degrees Celsius, I'll just substitute the Fahrenheit scale here on the left side of my equation. So I'll write 134 equals 9/5 degrees Celsius plus 32. This gives me that the degree Celsius temperature is equal to 134 minus 32, all multiplied by 5/9. So I can solve for the Celsius scale. I will get 56.7 degrees Celsius. Any questions here? Okay. I wanted to look at the next question, which is now a bit... Yes, Noor?
يعني بس بدنا نحول الفahrenheit للسلسيوس إنه بس نعملها inverse إنه بدل 9 على 5 5 على 9.
No. So be careful. What I did, let me just write it down again. I kept the same conversion, the same formula, because usually we give you how to go from degree Celsius to degree Fahrenheit. That's the unit that is given to you. Makes sense? Can you see my notes? So that's
Yes.
the formula. We're
Okay.
given the Fahrenheit temperature and asked to find the degree Celsius temperature. So what I want is this, and what I'm given is this. So I simply substituted here the degree Fahrenheit temperature and decided to solve for the degree Celsius temperature. To do so, I first isolated this number, brought it to the other side. And here I have the Celsius temperature. So I got 102 on this side and 9/5 degrees Celsius on this side. And then the degree Celsius temperature will be none other but 5/9 times 102. So what I did, I just like isolated the degree Celsius temperature. You can, of course, just write down a new formula where you say the degree Celsius is gonna be degree Fahrenheit minus 32 all multiplied by 5/9. But it's really not common to see this formula in formula sheets, you know? Usually this is the one that is given to you and you can really reform it to solve for the degree Celsius unit. Makes sense? Any other questions? All right, so let's take a look at the second question, which is a bit more mathematical. Here's my pen. So we're asked in question 5, at what temperature is the Fahrenheit scale reading equal to twice that of the Celsius scale, and in part B, half that of the Celsius scale? So there are special values at which actually the Fahrenheit scale will be equal to twice that of the Celsius scale. We can solve for that. So what we want is the degree Fahrenheit equals twice the degree Celsius. Now I know that also the degree Fahrenheit is equal to 9/5 degrees Celsius plus 32. So what I'm gonna do is I'll substitute this here. The fact that the degree Fahrenheit is 2 times the degree Celsius, I'll plug it here. And what remains is just to solve for the degree Celsius temperature. So I'll isolate the degree Celsius temperature on one side and keep the digits on the other side. And I'm gonna solve. Just open my calculator and solve for this. I have 2 minus 9 divided by 5. This is 0.2, hopefully. And I got that the temperature is 160 degrees Celsius. So when the temperature is 160 degrees Celsius, the Fahrenheit temperature is gonna be twice that, which is 320 degrees Fahrenheit. Does this make sense?
Yes.
Okay. So this was part A. Part B, same story, doing it again. The degree Fahrenheit is half that of the Celsius scale. So this is degree Celsius over 2, which brings us to plugging again. So I'll substitute the degree Fahrenheit by degree Celsius over 2. And here I'll have 9/5 degrees Celsius plus 32. Again, I'll isolate. So I'll have degrees Celsius over 2 minus 9/5 degrees Celsius equals plus 32. And this will give me minus 1.3 degrees Celsius equals 32. I got minus, so the temperature is minus 24.6 degrees Celsius. Does it make sense for temperature to be negative? Does it make sense that we got a negative temperature? So yeah, it's very normal to have temperatures below 0. Most ice is below 0 degrees Celsius and it will have negative temperatures. The thing is, both the degree Celsius and the degree Fahrenheit can be negative. But the Kelvin unit is always positive or equal to 0. Like the minimum value, the absolute 0 occurs at 0 Kelvin, and there isn't anything in nature that has a temperature below 0. You can ask me why, but I will not really explain this to a freshman course. That's something you would take in your next physics course if you go through a pre-med study or a physics major. Any questions? All right, now some questions on the thermal expansion, where I gave you the formula delta L equals alpha L0 delta T. So we're given at 20 degrees Celsius, a brass cube has edge length 30 centimeters. What is the increase in the surface area when it's heated from 20 degrees Celsius to 75 degrees Celsius? So I have the temperature change. Essentially, in question 8, I am given delta T, which is T final minus T initial. This is equal to 75 minus 20, which is 55 degrees Celsius. And I'm given the edge length at 20 degrees, which is 30. So we have this brass cube, and this is L0, which is 30 centimeter. We're interested in the area expansion. So what we want to study is not delta L, but delta A. Now we said delta A is beta A0 delta T. So the only difference is in the coefficient, which is beta, which is twice alpha really. And A0 rather than L0, so I will need the initial area. I am given the initial length, which is a bit tricky, but simply noticing that we need the initial area and that this is a cube, then the area is none other but the length squared. And this is going to be 30 centimeters squared. So I can solve for the initial area. This is 0.09 meters squared. So I can find the change in the area. Now the value of alpha usually is given to you, but in the book, they have a table of constants written at the beginning of the chapter, and then they use it everywhere. They don't keep copying it for every problem. So I'll just, you can just refer to that. So when practicing at home, obtain alpha from the table of constants. In chapter 18 in the book. So yes, I found the initial area and I found alpha to be 19 times 10 power minus 6. So the change in the area is going to be 2 times 19 times 10 power minus 6 times the initial area, which is 0.09, times delta T, which is 55. I want you to notice something. In physics, the SI unit of temperature is Kelvin. But for delta T, whenever you have a change in temperature, the change in temperature in Kelvin is the same as the change in temperature in degrees Celsius. Why? Because T in Kelvin is actually T in degrees Celsius plus 273.15. So if you're studying delta T, you're subtracting 273 twice, and then it doesn't really show up in delta T, so there's no conversion at all between delta T in Kelvin and delta T in degrees Celsius. I think I switched this. The Celsius is the Kelvin plus 273. Yeah, this makes more sense. No, it was fine. Sorry about that. I rarely memorize any formulas. All right, so from this, we deduce that delta T is the same for both. So I can leave this in degrees Celsius. I don't have to convert it. So I directly wrote delta T from here, and I can calculate delta A, and this is gonna be 11 times 10 power minus 4 meters squared, or 11 centimeters squared. One thing you should notice, so we found the increase in the surface area. Yeah, all looks good. So one thing we did also in the solution is that we accounted for 6 faces to check the increase in the area across all 6 faces. So what I found here was just for one face. And for the total surface area for the whole cube, it's like a bit more sophisticated. You have to account for the increase in the 6 faces. Okay, so let's check the next question, question 10. An aluminum flagpole is 33 meters high. By how much does its length increase as the temperature increases by 15 degrees Celsius? This is very easy. We're talking about a length increase here, so I will directly use delta L, which is L0 alpha delta T. The initial length of the flagpole is 33, so I'll substitute L0 by 33. Alpha is the coefficient of linear expansion of aluminum, which I will look up from the table. It's 23 times 10 power minus 6. Most coefficients of linear expansion are of the order of magnitude 10 minus 6, 10 minus 5 for solids. And delta T is the change in temperature. The increase in temperature is given to be 15. So this is delta T itself. Delta T is 15. We substitute that here, and we can find the change in the length of the aluminum ball. And number 11, what is the volume of a lead ball at 30 degrees Celsius if the ball's volume at 60 is 50 centimeter cubed? So I have V0 is 50 centimeters cubed when the temperature was 60. We want the volume when the temperature is 30. So initially what's given to me, I took it to be the initial volume and temperature, even if it's not, like I'm just assuming, because these are the quantities I know, so I can plug them in my formula, and I will use this formula, delta V equals V0 beta delta T, and V0 is the volume at the temperature of 60, so I'll plug here 50. So I can leave this in centimeters cubed, and then delta V will be centimeter cubed, rather than having to multiply by 10 power minus 6, which is quite annoying. But up to you. Beta is 3 times alpha, and alpha is found from the table of constants. It is 29 times 10 power minus 6. And delta T is the change in temperature. Here, pay attention, T final is 30, T initial is 60. So it's 30 minus 60. This is going to be a negative delta T. I will find the change in the volume. I'll just calculate that. So this is minus 0.13 centimeter cubed. One thing I want you to notice, the question asks for the volume of the lead ball at 30, and not the change in the volume when we go from 60 to 30. So what we want is V, not delta V, the final volume. Now I know delta V is none other but V minus V0, the final minus the initial volume. So V is gonna be delta V plus V0. Now delta V is minus 0.13 and V0 is 50. So I just found V, it is gonna be 50.13 centimeters cubed. Actually, it will be 40 something. I have to subtract here, yes. So I have 50 minus 0.13, 49.87. This is delta V. This is the final volume. This is the volume when the temperature is 30. Any questions?
دكتور
Yes.
مش لازم تكون في زيرو جاما أو بيتا نفس هيديك.
Okay, so yeah, sometimes I use different symbols from the book. Gamma is for the area. Yeah, so this here is gamma. All right.
Yes.
And for the volume, we use beta. Yeah, it's just a matter of symbol. What matters is that you're aware that one is twice alpha, the other is 3 times alpha. Any other questions? All right. I have this nice, easy question here. Find the change in the volume of an aluminum sphere with an initial radius of 10 centimeters when the sphere is heated from 0 to 100 degrees Celsius. So we want the change in the volume. To do so, we want delta V, which is V0 times beta times delta T, where beta is 3 alpha. And alpha, as usual, we find it from the table of constants. We look up the coefficient of thermal expansion for aluminum, which is here 23 times 10 power minus 6. Delta T is 100 minus 0. The sphere was heated from 0 degrees Celsius to 100. Pretty easy. The only thing I still need is the initial volume of the sphere. We are given the initial radius, and we want the initial volume out of that. So I'll just write the volume formula for a sphere, which is 4 over 3 pi r cubed. R is what's given to us, which is 10 centimeters. I can really leave that in centimeters and get my formula in, get my delta V in centimeter cubed as well. So I have here 4 divided by 3 times pi times 10 cubed, of course. This is around 4,200 centimeters cubed. And I'll plug this here then. So I'm gonna multiply by 3, then by 23, then by 100. And I got 29 times 10 power minus 6. Actually, the 10 minus 6 goes away. It's 29 centimeters cubed. This is the change in the volume of the sphere. Any questions? So this question, I'm gonna really skip it. It's a bit hard, so I don't really want you to study it for now. Okay, so now we're gonna be checking out our last phenomenon that we studied in this chapter, which is the heat energy absorbed and released when we have a change in temperature. Namely, the heat energy involved in a change in temperature is mc delta T. And if we have phase change, then the heat that is needed to attain this phase change is m times L. So what are we given here? One way to keep the contents of a garage from becoming too cold on a night when a severe sub-freezing temperature is forecast is to put a tub of water in the garage. If the mass of the water is 125 kilograms, so let's just write the given down, 125, and its initial temperature is 20, how much energy must the water transfer to the surrounding in order to freeze completely? So we're gonna check Q for the water to freeze completely. That's the question. Now, in these kinds of questions, whenever you have energy involved, and we have two formulas, as you can see, to decide which formulas to use, I'm gonna first make a diagram of the processes that are happening. What's my initial state? My initial state is water at 20 degrees Celsius. Now, the water is losing energy to the cold room. So this water at 20 degrees Celsius will become water at 0 degrees Celsius first. And in this state, the process that has occurred involves an energy Q equals mc delta T. Then the water at 0 degrees Celsius cannot cool further, although the room is at sub-freezing temperature, so it's below freezing, it's below zero. So the water now at 0 degrees Celsius is gonna start to freeze. It cannot go below 0 degrees Celsius. It will start to freeze. And I want it to completely freeze, which means I will have all of the water converted to ice at 0 degrees Celsius. To go from water at 0 degrees Celsius to ice at 0 degrees Celsius, the amount of energy involved is m times L. So Q, now I can solve my equation. Q is going to be the sum for all of the processes that I have written in my figure, and these are mc delta T plus ml. The mass is the same. All of the water cools down and then all of it froze. So I can take M as a common. The mass is 125, C is 4186, and delta T is, well, 0 minus 20. And the latent heat of fusion, I can look it up from the table of constants again. 333 times 10 power 3 joules per kilograms. And I'll just calculate the total Q. This will be 5.2 times 10 power 7 joules. In part B, what is the lowest possible temperature of the water and its surrounding until that happens? So for all the water to freeze, I need the temperature to be 0 degrees Celsius, definitely. Otherwise, there will be no equilibrium between the room and the water. So for the lowest possible temperature for the water is 0. Below this temperature, the water must have already all turned into ice, and that is convenient. So what we're doing here is to keep objects from becoming too cold and below degrees Celsius temperatures, we place them in water. And then for them to reach 0, all of the water must already freeze. So to protect objects from low temperatures, we just dip them in water. They will stay in equilibrium with the water. They will always have the same temperature of the water. And the lowest the temperature of water can go is 0 degrees Celsius. The objects will never go below 0. Unless all of the water froze. And for all of the water to freeze, we really need a lot of energy to be taken from the surrounding. So the surrounding has to be at a quite cool temperature. Any questions here? Okay, let's look at this nice easy question. We have a small electric immersion heater is used to heat 100 grams of water for a cup of instant coffee. The heater is labeled 200 watts, which means it converts electrical energy to thermal energy at this rate. So this is the power, 200 watts. What does this power means? The electrical energy is converted to thermal energy at this rate. Rate means we're dividing by time. So this is the energy over time. So this is Q over T. We're heating 100 grams of water, so M is 100 grams. Calculate the time required. We want T, and I want to see that T shows up in this formula, actually. We want the time required to bring all of this water from 23 degrees Celsius to 100 degrees Celsius. So T0 is 23, and T final is 100. Ignore any heat losses to the surrounding. So what I'm gonna do is I'll say, okay, the power is Q over T, and the power is 200 watts. This is given to us. Q is MC delta T. T is the time is what we want, so I'll just rearrange for the time. The mass of the water, I know it, 100 grams, which is 0.1 kilograms. C is the specific heat of water, which is 4186. Delta T is the change in temperature. We're going from 23 to 100. And the power rating is 200. I'll substitute that. You can solve for the time. You'll get 160 seconds, which is a bit less than 3 minutes to heat up 100 grams of water using this heater. Any questions? Just trying to pick something else. Let's check try question 27. 27 is nice and similar to what we were solving. Then we can move on to harder stuff. So we want the minimum amount of energy in joules required to completely melt 130 grams of silver initially at 15 degrees Celsius. So we have the mass, 130 grams, and the initial temperature is 15 degrees Celsius, and we want complete melting. We want Q for complete melting. So, like I told you, when we want to find Q, it's best to start with the diagram so that we can have all of the processes in front of us and know whether we should include ML, MC delta T, more than that, something else. Sometimes we have two-phase changes. If I have a solid and I want to completely vaporize it, then you'll put ML for melting, then ML for vaporization. So the diagram can be helpful. So I'll have my initial state, which is silver, solid at 15 degrees Celsius. Now I want to go to the melting point. What I'm gonna do is, one, I have to check the temperature of the melting point of silver so that I can know my final temperature. So the melting point of silver, let me check out. It's given here in the solution in Kelvin, but I prefer to write it down in degrees Celsius and keep everything in degrees Celsius. So this is 962 degrees Celsius. I'm gonna write it down. Okay, so this is given, of course. So for the silver to melt, it has to first go to the melting point. So we're heating here. And I will have silver still solid, but at 962 degrees Celsius. To go from 15 to the melting point, an energy MC delta T is involved. And then I want the solid silver to completely melt. Now it is at the melting point. So I'm gonna have now the silver all melted. It will be in liquid phase, also at 962 degrees Celsius. And to melt the silver, I will need an energy of ml. So I can now find Q. Step 2, I'll just add all of the energies. I will have mc delta T plus ml. This is going to be 130 into the specific heat of silver. We can also look it up. 236. Delta T is 962 minus 15. Remember, always put the final temperature minus the initial. The latent heat, I'll look up the latent heat of fusion of silver. This is 105 times 10 power 3. I will calculate this and find the total Q. This is 4.27 times 10 power 4 joules.